So I'm redoing the videos from section 2 because it didn't look like you could see them very well. So section 2 has tables, and they're really very easy once you get the hang of what they're talking about. So in this one you can use a graphing calculator. It gives you a table and it tells you that WT is measured in Fahrenheit, and it's talking about the temperature of water in a tub, and it's strictly increasing. And at 0 the temperature is 55 degrees. The water is heated for 30 minutes, beginning at T0, and values of WT for the first 20 minutes are given in the table. So it says use the data in the table to estimate the first derivative of 12, show the computations. Now, you don't have a function rule, you don't have a graph. So what you want to do is use your slope formula. So where does 12 fall between 9 and 15? So you're going to go W of 15 minus W of 9, 15 over 9, and you're going to get 1.017 Fahrenheit divided by minutes, and that's the rate that the water is increasing at time equal 12 hours. Now, it says use the data to estimate 0 to 20 of W prime t, so the first derivative. Using correct units, interpret the meaning of this. Now remember first fundamental theorem of calculus. So you're taking the integral of the derivative. So it's just going to end up being W of 20 minus W of 0. So when you're taking the integral of the derivative, it's this back to the original, W20 minus W0. So you just come up here from your table and get 71 minus 15, and you get 16 degrees. And that's the temperature that the water is warmed to over the interval from 0 to 20 minutes. Now part C says from 0 temperature, the average temperature is 120. Use a left Riemann sum with 4 sum intervals indicated. And does this approximate an overestimate or an underestimate? Okay, so you're going to look at your chart, and you've got 4 subintervals. So you got here, 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 and here. And you want to write Riemann sum. So remember, the width of your little rectangles is the difference in your x values. And so you're just going to say the first one's going to be the width of 4 times the right value, which is, no, it said left, I'm sorry. I was going to say I've got 55 there. So it's the left Riemann sum. So you're going to do 4 times 55 plus, then you're going to do 5 times 57, 6 times 61, 5 times 67.9, and that's multiplied by 1 over 20 because you had the average there. And you would do all that and you get 60.79. Now, since this is an increasing function, so think about the shape of an increasing function, the left Riemann sum is going to be an underestimate because the left value would be lower. And then part D says for 20 to 25, the function W models the water temperature first derivative given by, and they give you a function rule. Based on this model, what is the temperature of the water at T equal 25? So you're going to do your starting temperature at 20, which came from your chart, 71, going from 20 to 25, WT. Remember, when we do that, the same thing as W of 25, and it's going to be 73.043. And you can use Math 9 for this because you can use a graphing calculator. Now let's look at the next one, 2011. You're talking about the T cooling. The temperature of the T is modeled by this function. T's in minutes, H of T's Celsius, and they give you the values. So it's talking about the pot of tea cooling. So it says use the data in the table to approximate the rate at which the temperature of the tea is changing at time 3.5. Show the computations that led to your answer. So again, you've got a chart. You don't have 3.5, but it falls between what, 2 and 5. So you're going to do h of 5 minus h of 2 over 5 minus 2. Work that out, and you get negative 2.667. So again, this is on a calculator one, so you can use your calculator. So B says, using correct units, explain the meaning of 1/10 of h of t, and use a trapezoidal sum with 4 subintervals. So remember, your trapezoid formula is 1/2 h, b1, b2. And so we got 4 subintervals from here, 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 and here. So a trapezoid, the height is going to be the difference in the x's, and then you're going to just use each base. So you got the 1/10 out, you got 1/2 part of the formula. The first inverse is 2 times each of the values, plus 3 times each of the values, plus 4, plus 1. So those came from the differences here, and then your base, you have 2 bases of each trapezoid. So if you do all of that, you get 52.95 is your average temperature of tea in Celsius in 10 minutes. So I hope you're starting to see these are pretty easy ones. So it says evaluate 0, 10, h prime of t using correct units, explain the meaning. So again, you don't have a function rule, but you know when you take the integral derivative, it's just h of 10 minus h of 0, so that comes straight from the chart. And that's the temperature drop in Celsius from 0 to 10 minutes. And part D says, at time equals 0, biscuits with a temperature of 100 degrees Celsius were removed from the oven. The temperature of the biscuits is modeled by this function. Using the given model at t equal 10, how much cooler are the biscuits than the t? So the t at 10 is 43 degrees. Now, how do we find the biscuits? We start with what it comes out of the oven, 0 to 10 of this. This is on a calculator active, so you know the function rule, so you can do math 9. And so h of 10 was 43, this was 34, and so the biscuits are 8.817 degrees Celsius cooler than the tea. So the next one is 2011. It's talking about Ben riding his bicycle. So B of t is his position function, and V of t is his velocity function. And says, use the data in the table to approximate Ben's acceleration at 5 seconds. So you're going to look at your velocity and at t equal 5 seconds, indicate units of measure. So we're going to come up here, and 5 is going to fall between what? 0 and 10. So you're going to go V of 10 minus V of 0, 10 minus 0, and you're going to pull your values from this line. So you're going to get 0.03 meters per second squared. Now this one's a non-calculator one. So using correct units, interpret the meaning from 0 to 60 of the absolute value of V of t. Approximate using a left Riemann sum by the day. Okay, so absolute value of V of t, the integral is total distance. So that's the total distance traveled. And if we're going to do a left Riemann sum, so we've got 1, 2, 3 subintervals. So our width is 10, and we are doing absolute value of velocity. So we're going to come down here, 10, and we're using 2, and then the next one's 30, and we're using 2.3, and 20, and we're using 2.5. So you get 139 meters. Now part C says from 40 to 60 must be a time when Ben's velocity is 2 meters per second. Justify your answer. So the mean value theorem said that there's a derivative that's equal to B of B minus B of A. So I want to find, it talked about when Ben's velocity is 2 meters per second. So V of t is the first derivative of B prime of t. So I'm going to do B of 60 minus B of 40, and you're going to get that from your B of t line. And so if you do that, it equals 2. So since this is a differentiable function the whole way, mean value theorem says there is a point, and we prove that it equals 2. Now, part D says a light directly above the track. The distance L of t between Ben and the light satisfies this function. LT squared equals 12 squared plus BT squared. At what rate is the distance between Ben and the light changing? So we want to know the rate it's changing, so we're going to take the derivative. So we're going to do chain rule, 2 of L of t times the derivative of the inside. Derivative of 12 is 0. 2 of B of t, B prime t. So we've got this formula. Now we want to isolate L prime t because that's the rate we're trying to get. So I'm going to divide this over. My 2's are going to cancel out. The value's at 40, so B of 40 comes from your chart. B prime of 40, because that's velocity, comes from your chart. So they come right from your chart. Now you need to know what L of 40 is. So if you go back to your original equation, you got LT squared was this. So if I take the square root of that, I get 144 plus B of t squared. Well, if I put 40 in there and square, you get that value from your table. You get 144 plus 81, and you get 15. So I can come back and substitute 15 in for this, do my math, and I'm going to get 1.5 meters per second.